So the next speaker is Alok Laddha from CMI, and he's going to tell us about Associahedron, Corolla polynomial, and the Yang-Mills S matrix. Go ahead, Alok.
Okay, so first of all, I should apologize because my talk is way out of the theme of this conference. But hopefully, I mean, there is a talk about Q of T, so I kind of use the fact that the title has Q of T, the title of the workshop, and I hope at least it will have some information. So maybe. So okay, so this is the title of my talk, and maybe one context for where I can justify the talk in this conference is this talk by this quote by Andre Mata, who said that one can never be sure to have exploited all the axioms of quantum field theory. So it's in that spirit that you should take this talk as far as this workshop goes. So I should of course thank, but Onkar and Suvrat, or maybe not thank to tell me to give a talk, but at least inviting me to this very nice conference. So maybe I will start here. So let me start with some motivation for what the talk is all going to be about. And the talk really fits into this new program which has started maybe 7 or 8 years ago, which roughly is called Positive Geometry program to define to classify S matrices. And let me give a rough idea of where the basic motivation of the program goes. So even for last 20 years, we have learned that we have learned many different ways to compute amplitudes. Like, so for example, let me just give a rough a few examples. Even for tree level amplitudes, in which is like the very bare bone thing from the perspective of ordinary quantum field theory, we have many far more efficient way than Feynman diagrams to compute these amplitudes. So two of them, for example, are what are called recursion relations, and the other one is what is called a worldsheet formula. So this is a worldsheet formula, so it looks like a string theory formula, but it's really a formula to compute tree level amplitudes in gauge theories and gravity. And what is remarkable about this formula is that they kind of sacrifice some of the basic postulates of quantum field theory that we take for granted. So in the usual old S matrix, or in our usual S matrix program, some postulates are considered to be fundamental. And those are, as everyone knows, it's point. So for example, if you are doing flat space S matrix, then Poincare invariance, unitarity, locality, and there is a slightly thorny postulate which requires a far more longer discussion because it is often used in slightly different ways. But let me just call it analyticity of the S matrix. So as a function of Mandelstam variables, we expect this S matrix to have some analytic properties away from where it has poles and branch cuts. But if you look at these recursion relations, for example, even for tree level amplitudes, we see that they start sacrificing some of these postulates while building the amplitude. So for example, BCFW recursion relation, it compromises locality. So it builds S matrices from lower point amplitudes where particles always remain on shell. So there are no fields now in the game when you build these amplitudes, and so obviously in the intermediate steps of a calculation you will not have locality. So if you look at this recursion method to build amplitudes, like say endpoint amplitude from lower point amplitudes, you will see if you stop at some intermediate step, it will look like this is not an amplitude of a local quantum field theory. But of course, in the end, finally, when you complete the calculation and stare at it, you will see that even though it may not look local, in the end it is local amplitude. And the CHY formula is even more remarkable because it's really like the string theory formula. So if you want to do a tree level amplitude, you should really, the whole idea is to look at some integrands on moduli space of n punctured Riemann sphere, and then from these integrands you can show that if you integrate them along this moduli space, you get these tree level amplitudes. And so this formula is even more striking because it sacrifices both unitarity and locality. And so both this unitarity and locality are really encoded in the geometry of the moduli space, the boundary structure of the moduli space. So in that sense, it seems like some of the more powerful methods to compute amplitudes in last 20-25 years sort of question that, maybe the postulates that we considered fundamental are actually emergent for some more fundamental postulate. So it's in that spirit to sort of synthesize these kind of different avatars of S matrix that this program of positive geometry emerged. And here the idea is that we don't start from anything except Poincare invariance and see how far we can go. So this sounds like a really silly statement, but I hope to convince you that you can get quite interesting statements thanks to completely independent work in the branch of mathematics. Of course, there's some conservation of work, right? So we have to use some results from some other branch. Usually we turn to math, but we will only assume Poincare invariance, neither unitarity or locality, if we are looking at the T-level amplitudes, and we will see how these things emerge and what kind of S matrices we sort of can compute out of without looking at Lagrangian or recursion or even CHY formula. So please stop me at any time if there are any questions. But so because I may run out of time, let me tell you the main results that we will find with the schematic results, and then I'll spend some time explaining some of these results in some detail. So here is the picture that we will see, that in the space of Mandelstam, so I will always call this kinematic space. So this is the n particle Mandelstam space. And so this space only assumes Poincare invariance. We haven't assumed anything else. And we will see that in this space, hopefully in the end of the talk, that we will find some convex geometries. So let me just sketchily draw them like this, such that these geometries will be such that they will always have lots of boundaries, and these geometries themselves will induce some forms. They will induce some forms, differential forms on the whole kinematic space. And it will turn out that, so these forms will be uniquely defined by these geometries, as we will see. These are some results in algebraic geometry. And then it will turn out that if I take these forms and I restrict them to this geometry, so let me call this geometry M, I will restrict it to M, then often it will give me amplitude of some theory. So, this would be an idea that we are kind of starting with a very empty kinematic space, and we will see that there are some polytopes waiting to be found, these geometries. And if we study these geometries in detail, we start getting S matrices of local quantum field theory for tree-level amplitudes. So that would be the first sort of results, and then we will see how this program is not enough to obtain gauge theory amplitudes. In the sense that there will be no form whose restriction on such polytopes will give us gauge theory amplitudes. But as we will see that there will be some tensor fields which will also geometrically emerge on Kn, and whose contraction with these forms will give us gauge theory amplitudes. So, and I should say that everything I'm saying is completely well understood up to one loop integrand of these S matrices. So I will at least indicate the results up to one loop, if at least in the end. And for all the theories, not the gauge theory, but for all the scalar theories, in last few years we have striking results to get all loop integrands from these kind of geometries. So maybe if I have some time, I will indicate at least the main results that we now understand for example, scalar field theory with arbitrary polynomial interaction to any loop order. So if there is any question, please stop me. Yeah.
So one of the first example of positive geometry, something for any plus
Yeah, thanks. So that's a very good point. I should have said that. So actually, if the first example is not n equal to 4 super Yang-Mills, ironically, first example was ordinary Yang-Mills, and it was shown that the what are called maximal helicity violating amplitudes can be thought of as volumes of some polytopes in some auxiliary kinematic space. That was way before. So that gave rise to amplitude-hidden, what is called program. But I will shy away from this. So because I will just talk about non-supersymmetric gauge theories.
Okay.
Yeah.
But what do you mean not like the volume? Park-Taylor is the volume of something, and then you're saying the volume is not enough to obtain Yang-Mills amplitudes.
Right, because Park-Taylor is not enough to obtain Yang-Mills amplitude.
Oh.
Park-Taylor only gives us scalar amplitude in the way you are phrasing it.
Oh, okay.
Okay. So please ask me if there is any question. So let me start. So that's the, we don't want to assume anything except Poincare invariance. So then in that sense, we are a little bit in trouble because all we have is this kinematic space. So we will see how much we can, how much structures we can induce in this without assuming any physics. So let me first start with just some basic convention. So one very good basis for kinematic space of Mandelstam invariance is the following basis. So you like fix an order of your particles 1 to n, and then just define this kind of this particular combination of Mandelstam. So you start from pi, and if I is less than j, go all the way to pj minus 1 and square it. So this, as you can see, this is some generalization of Mandelstam invariance. But these are always planar, as you can see, because we have assumed an ordering. You may think that these kind of variables are not enough to get all S matrices like without without plenarity, but that's not true. It's just a good basis. So one can show that the full Mandelstam space can be coordinatized here, can be coordinatized in terms of these variables. So the dimension of this Mandelstam space, if you are n particles, is this, and you can immediately check that all possible chords you can draw, internal chords you can draw, is also of this number. So then you have a very good basis, and this basis has a good geometric interpretation. But now our idea is that this basis is barren, this space is barren, we don't have anything here, because we have already taken care of Poincare invariance. And so how we can find things like structures like S matrices and meromorphic functions in this space. So an interesting thing occurs though already at this stage. So let's take a concrete example of n equal to 5, and you can check immediately that the kinematic space will be 5-dimensional. But let me now forget about the kinematic space. Let me not worry about the fact that there are these x's have physical meaning in terms of momenta, but let's just look at a Cartesian space. So it will have 5 coordinates, and I'm simply labeling these coordinates exactly in the way that these Mandelstam invariants are labeled. So, but these x's have no relationship, they are just coordinates. So 5 x's, I have labeled them as x13, x14, and then the remaining ones, x35, x25, x45. And so this is now we have kind of divorced ourselves from physics. So anything we find here without invoking physics principle, if it can give us some S matrices, then that would be an interesting result for us. So for some time now, we are going to only focus on this space, which is just some Cartesian space labeled by these coordinates. And now here something really remarkable happens, that if you look at, so these x's clearly have some nice pictorial meaning, because if I draw this x13, I can always think of it as a chord which goes from some 1 to 3 on some abstract polygon. So this polygon, this has no physics meaning. It is just some totally abstract concept I'm drawing just to visualize what these chords are. So it's kind of a trivial thing, and I've labeled these vertices as 1 tilde, 2 tilde, just as a convention. And now here's so you may think, so what? I mean, so I have 5 chords here. How much can I do with it? But there are some developments in algebraic combinatorics and in quiver representation theory which gave some striking result, and the result is simply the following, and this will be heart of the structures that we will find. If you give me any chord which is labeled by vertices I and j, I can associate to it a vector which I'm going to call g, and this g simply comes by some looking at the intersection of different chords, how they intersect, in how many points they intersect, etc. So we will of course not go into it. You can trust me that this correspondence is a math result. And so for this example, particular example, if you start with this as your basic chord, so you fix these chords as 1, 3 and 1, 4, then it turns out that you don't have to look at the full 5-dimensional space. Already in this space is completely spanned, this 2-dimensional space of 1, 3 and 1, 4 is spanned by all the vectors that you could assign to all the chords. So you see that there are 5 vectors here, 1, 3, 1, 4, 2, 4, 2, 5, 3, 5, and they are totally spanning this 2-dimensional space. So this result is striking in the sense that this is true for any n, in the sense that, if let me give another example. So here is another example. So if you don't start with, so these chords are special because they're fully splitting your pentagon into 3 triangles. But you can ask, okay, what if I didn't do this? What if I only took 1 chord? Do I still get some span of subspace of the full kinematic space? And indeed you get. So if you just start with 1, 3, then the results in quiver theory will tell you that you get, it will span for you a full real line where the positive direction is spanned by the vector associated to 1, 3, and the negative direction is spanned by the vector associated to 2, 5. And 2, 5, as you can see, is kind of intersecting this 1, 3. So the basic idea is that if you fix any subset of chords which are not internally cutting, they will span for you a subspace of the full kinematic space, and that subspace will be of the dimension, which is the number of chords you have drawn. So I hope this point is clear. So here we start with 2 chords, and it spanned a 2-dimensional space, these vectors. Here we start with one chord and we get a one-dimensional space. And just as a convention, these are called G vectors, and they are like stars of the show for us. Yeah.
Even at this kinematic level, your kinematics of color ordered amplitudes, right?
No, not yet.
Not yet, but
No.
haven't you fixed the ordering of
No,
1
no,
to n,
no,
not
no.
even a cyclic ordering?
No, just to fix basis. So even for, just to give you an example, so in the n equal to 4 case, we have three variables, right? S, T and U. But of course, we know for massless particles, say U is minus S minus T. So independent basis is S and T, which is simply P1 plus P2 square and P2 plus P3 square. So that is just to fix a basis. I haven't assumed any planarity or anything. I don't have any particles or anything right now, it's just some.
But
Yeah.
you have some number, you're saying in this, you can do any permutation of the vertices. You don't have to do a cyclic permutation.
Yeah, you can, you don't have to, I'm saying you don't have to do the permutation. If you fix one ordering, any one ordering, and look at all these, they are basis for all Mandelstam invariants. Like here, right? Yeah, that's all, right now it was only that. So the basis is this basis. You could have chosen non-planar basis as you are saying, but we are just choosing this basis because they have nice geometric meaning in terms of these chords. Yeah. Okay, so now the point is that, okay, so far we don't really have much, we just said that.
Sorry, can I ask a
Yeah.
I didn't understand the two-dimensional
Yeah.
plot in the bottom. Like, what are you say that the 5 vectors all end up in a two-dimensional space. What are the coordinates in that space?
Yeah, exactly. So if I start with the coordinates are just some, I'm just labeling coordinates as x13 and x14, for example. And let us say that I start with this as my, so I have to start with some chords. So like I started with this chord, I fix these chords. Once I fix these chords, then for any other chord, I get a vector which is spanned in this two-dimensional space labeled by 1, 3 and 1, 4. Maybe I give an example that will make it clear. Let me just quickly give an example. So that, yeah, because this is kind of central for us. So let me give an example and explicitly work it out, what I mean by this. So let's consider a more simple case, which is n equal to 4, which is the simplest case. So let's just take, so this, so let's fix this as a chord, this one. And now you see that, so what I'm saying is the following. So now I'm telling you how to put an assignment of these G vectors once you fix this chord. So let me just tell you the assignment that comes from quiver theory. So one way to understand this assignment is, let's just draw in each of these triangles, let's just draw some orientation. So we have to be just consistent. You can choose any orientation. So if you choose clockwise in both cells, then this is what you find. This is the figure you find. Now you see that if you look at this chord, which is, which is at this vertex, let me call this vertex 1 because it follows 1. So if we look at this chord and this chord, then both these edges are outgoing. So then I assign to this a vector, but it's only in one dimension because I have only one chord to begin with, so I assign vector 1. But if you look at 2, 4, so this is 2 and this is 4, then these two are incoming. So then G24 is -1 because both are incoming. So that's the assignment. So you see that both, so now we started with a two-dimensional space, which was x13 and x24 as our kinematic space in 4 for n equal to 4. But this G vector span only this space. Is that help? Is that what you're asking, or? So once you, all the G vectors will lie in the space, the dimension space spanned by the number of chords you drew to begin with. Is that okay? Or?
So the vectors live in the span the x1 free line on this graph. So
Yeah, no, it's just that G13 is just, it's just G13 is just 1 in the sense that if I choose G13 is the unit vector spanning x13, they are just anti-parallel to each other. So once I fix, because I fixed one reference chord, once I say that G13 is a unit vector along x13, once I just fix that, then G24 becomes the one which is in the opposite direction. That's all. Right?
So you're sort of living on the space where x13 is equal to minus x24. That's what you're saying. So
yeah, I haven't come to that yet, but yeah, you are right. I mean, so far
kind of living on that.
Yeah, thanks, exactly. Yeah, but I haven't. Yeah, you are right, absolutely. So these just these combinatorics will give us this kind of structure so far, And let me just quickly say why I'm doing all this. I mean, you may already be a bit annoyed, but the point is that once you give me, so what is remarkable about this is that this structure is very robust, in the sense that even if I look at like an abstract, so we started with this abstract polygon, like abstract pentagon, and you could even put a hole here, abstract pentagon with a hole, and you could then start asking that, okay, let me look at all possible, let me look at like a dissection of this whole pentagon, like I did in the previous case, which means I'll have to start here, for example. So let me start with this as my reference. And then again, you could look at all possible chords, but now you will have more complicated chords. You could have chords which could go like this, because the topology is not trivial. With all of them, you will associate a G vector, and it will always lie in a 5-dimensional space spanned by 5-dimensional space, which would be, for example, I could label the 5 axes as xi0, where this is 0. So the point is that once you fix some chords, then that will determine for you G vectors for all other chords. And it will always lie in the space which has the same dimension as the number of chords you fixed, and I could just choose to label my initial chords as the variables that I'm spanning. So that's just a convention. Yes, so this structure is very, very robust, and what this buys you is a absolutely remarkable, I feel, result, is that if you now ask, okay, what is a polytope or a geometry whose all the normals to the faces are precisely these vectors? So this is a question now I'm asking. I'm still not in the physical space, I'm only in this space. And I'm asking a question, what is a geometry which is such that its faces, so it should have 5 faces because there are 5 normals, and the 5 normals are precisely these ones. And this uniquely fixes up to the origin, so it could be anywhere, but up to the choice of the origin, it uniquely fixes the shape of the geometry. And this shape of the geometry is rather remarkable. So if just for convenience, if I choose this origin to be at 0 of this space, but we don't have to do it, and we will see that this, where we put it will generate mass of the S matrix later. But let's say that I just locate my polytope here. So up to the choice of origin, up to the choice of one of the vertex, this geometry is completely fixed by this fan of vectors, such that these boundaries are precisely, so this boundary is x14 equal to 0. So it's a linear geometry, right? Of 2 dimensions, it's living in 5-dimensional space, which means it must have come from 3 linear equations. So it will chart out some boundaries, and these boundaries are, in this case, okay, so at least something nice has happened. So I hope that this part is clear, that we started with an empty kinematic space, then as Suvrat asked, we choose a basis. We could have chosen other basis, but we could have also chosen this basis. This is usually called planar basis because of exactly Suvrat said we had to fix a choice of ordering. But once we started with this basis, we saw that if I just thought of this as an abstract kinematic space, then just the fact that these basis vectors can be thought of as these chords, combinatorial chords, they gave us concrete geometries inside this space. So far we are still not close to physics, but we see that some structures have started emerging. And this particular structure is called an associahedron. And this result, let me now write down the result for any n. I was just showing an example for n equal to 5, but we can do it for any n. And so, 15 minutes. Okay, I will just go very, very fast. So for any n, this abstract kinematic space, which has dimension n into n minus 3 by 2, there is a unique associahedron that lives. So I am again schematically drawing it. Of course, it is going to be complicated geometry and of higher dimension, but it's completely fixed by the Xij chords or G vectors. So at least this point I want you to appreciate that we haven't assumed anything. I mean, we used some results from representation theory of quivers, and that gave us interesting convex geometries in this space. And the dimension of this polytope, as you would see from this example, right, that here we got a 2-dimensional geometry because we needed 2 chords to dissect our pentagon. So if you have a n gon, then the dimension will be n minus 3, as you could see, because you need n minus 3 chords to dissect the n gon. So this will be n minus 3 dimensional. Okay, and now quickly I will tell you what this buys us. This gives us, thanks to the, so these geometries have some incredible properties. So let me just write two properties which will be useful for us. So it has some fundamental properties which really look quite striking. So one property is that any boundary of associahedron is always an associahedron is always product of associahedra. What I mean by this is simply the following, that if you have a three-dimensional associahedron A3, then it will never have a boundary which is, so if you look at A3 and look at any boundary of A3, then you will see that it has either a boundary which is a square, so the boundary is either a square or a pentagon. It never has a boundary which is a hexagon. And the reason is that, as you can see, that I didn't draw the one-dimensional associahedron. I drew the two-dimensional associahedron, which was a pentagon. But if you do the same procedure for one-dimensional associahedron, it comes out to be a one-dimensional line. And of course, zero-dimensional associahedron is simply a point, because that is simply coming from a triangle which has no chords at all. So you can see that this boundary is just a product of A1 and A1, and this boundary is a product of A2 and A0. But you will never get an hexagon. And this structure is robust. So if you go to any dimensional associahedron, you will see that you would never get a boundary which cannot be induced from products of lower dimensional associahedra. And if you think for a minute about it, this is exactly what happens because of unitarity for tree-level amplitudes, right? That if you go on shell on any propagator, it always breaks into the sub-amplitudes of the same theory that you started with. Now let me quickly tell you how we get S matrix from here, and what kind of S matrix is, because right now there is no physics. So it's just math. And now we need just one more result from algebraic geometry, which is the following. Oh, sorry, I wanted to write just one more fundamental property. So the second property is that all associahedra are what are called simple polytopes. By this I simply mean that if you take any vertex of the associahedra, then the number of faces adjacent to it is exactly n minus 3. So if the dimension of this is n minus 3, and you take any vertex, then number of faces touching this vertex is exactly n minus 3. And so that's this property. And thanks to both of these properties, there's a nice result in algebraic geometry which says that existence. So I'm just writing it, schematically. Existence of an minus 3 inside this Cartesian space induces a unique form which has singularities, which has simple poles on all the boundaries of the associahedron. So let me just write what this form is, and after that we will see how we can start getting S matrices from here. So this form is very simple expression to write down. So just keep in mind that every vertex of this associahedron, so if there is a vertex V here, it is completely determined by some G vectors like this. So in this case, for example, there is a vertex here, as you can see, which is intersection of 3, 5 and 2, 5. This one is 2, 5 and 2, 4, etc. So every vertex is labeled by some triangulation of your n-gon. And so let's say that this triangulation is some chords x13, x14, ... And so then this form is of the following type. You sum over all the vertices of the associahedra and you pick one sign for one vertex, so you just call it +1. So that sign is ambiguous, but once you fix it, then for every other vertex you start doing appropriate mutations like this. I will explain what I mean by this in a minute. And then you do d log xij and you just wedge over all the chords which belong to the vertex. So again, let me repeat. Every vertex corresponds to n minus 3 chords. And so you take all those chords which correspond to one vertex and then you just do this operation. And what this mod v is, it's simply the distance that you travel from a reference vertex. So let's say you chose this as your original vertex. Then if you go to, if the next vertex is just next to it, one next to it, then you put minus, just to be plus 1. If you need to go to 2 swaps to go here, then you have to put 2 here and things like that. So that gives you the sum. So this form is fixed up to an overall sign. Okay, so Raghu, how much time I have? 9 minutes. Okay, 9 minutes, no problem. So now, okay, so now we come back to physics. So now, okay, so what we have is some geometries, convex geometries, linear polytopes, and some forms which are meromorphic. And now we can go to now we can do with physics. So now we can go back to the Mandelstam space. So now we have 2 spaces and the kinematic space. And of course, you can say that, okay, these spaces are just different, so I could do any diffeomorphism between them. But let's start with simplest diffeomorphism. So let's say that we look at linear diffeomorphisms. So the idea is we have some structures here, some geometries and some form, and now we are going to map those structures here. But now there is a complete choice, right? I could have started with any diffeomorphism. So let's start with the simplest diffeomorphism, by which I simply mean that we could take xij to be some sum over all kl where alphas and betas are constants, are real. Then what will happen if you take this this kind of linear map and you start mapping this associahedra, you will get some deformed associahedra, and the form will get, if it's a diffeomorphism, using the inverse you can pull it back and you will get some form here. So let me just write it like this. Okay, and now the question we want to ask is, for any such diffeomorphism, because this form is over all space. So let's do the first thing, simplest thing we could do, which is to look at the restriction of this form on this associahedron. So I take this form and I restrict it to my an minus 3, which actually it's phi of an minus 3. Okay, so this is the object we can play with, because it's the object that we found by simply doing some quiver stuff here, and then then we got something which was totally universal, and then we could have started with any diffeomorphism and mapped it onto kinematic space. So starting with a barren kinematic space, thanks to results in math, we found some geometric structures. We still don't know what it has anything to do with S matrix, but okay, it's interesting. We found some life inside the kinematic space. Now, okay, so let's look at simplest diffeomorphism, which is trivial. So let's take xij equal to xij, identity diffeomorphism. And now if I do this, so my phi is identity. So now if I do this, and I just restrict it, which basically means I just call all the small x's as capital X's. So that's the choice of diffeomorphism. Then this thing turns out to be so let's take an example, because I'm running out of time, of n equal to 5 again. So this thing turns out to be, there are 5 terms. Sorry, I should have written capital X, but because it's identity diffeomorphism, it doesn't matter. And you can ask, okay, is this function, which is meromorphic, is it S matrix of any theory? And it turns out that it is. There is a specific theory, which as Suvrat was mentioning, it's called okay, I won't go into detail, it's a colored scalar theory. So it's a theory of massless scalars, which has 2 adjoint indices. And it has interactions of this type. Okay, we could put some different structure functions for both groups. and then trace of this. And so then that, if you take this theory, and of course there's a kinetic term I didn't write down, and then you look at the S matrices, all the S matrices in this theory are kind of built out of these objects. So these are what are called color ordered S matrices. They are good S matrices in their own right. And all of them come out of this choosing the identity diffeomorphism. But we didn't have to do this. We could have taken other diffeomorphisms. And that's quite interesting because more complicated diffeomorphisms you choose, you always land up with some cubic scalar S matrix where you could have different scalar fields with different masses. So sorry, I ran out of time, but let me just give one result. So this was a result that we derived with my fantastic collaborator, Brunmai, in 22, 21 and 22. And we showed that, for example, there is a choice of this linear diffeomorphism, which is such that it will give you, if you have this theory, so you take that, you compute this, and now you ask the question, is it amplitude of any theory? And you consider, once again, you consider colored scalars, but consider two of them, phi1 and phi2. And then you look at the following interaction. Where phi1 is massless, and let's say phi2 is massive, so phi2 is not equal to it. Then you can show that there are a class of these betas and alphas which give you tree-level amplitudes for this class of theories. But this is an interesting result because our seed polytope is the same. It's a universal associahedron. We didn't change anything here. So different S matrices of different theories, including theories with more than one scalar, are sort of contained, the information is contained in the choice of these diffeomorphisms. Okay, I have run out of time for the Yang-Mills. Maybe I take 1 minute. I have 3 minutes. Okay. So I just quickly say something about Yang-Mills then. Yeah.
Why? What is the physics? Why does this work? I mean, sure, we do this and we find these positive forms turn into amplitude.
Yeah.
But in the other, why do we expect it to work?
The reason we expect it to work is in something the same reason we expected. We understood why CHY works. So this associahedron have two properties. One is that as I was saying, any boundary of the associahedron is product of lower associahedra. So that's exactly what happens in unitarity. And the meromorphic forms that algebraic geometry gives us on the simple polytopes are such that they are precisely this D log form. So they are forms of the type dx by x minus dy by y, these kind of forms. So the fact that they have simple poles only on the boundary and the fact that boundary factorizes, both are properties of unitarian locality for tree-level amplitudes. So that structure is encoded here. But the interesting part is that I think the interesting part is that there is a universality. I mean, naively we would not think that there is any connection between massless phi cube theory and a Yukawa type theory with arbitrary couplings, right? But we now see that they are kind of coordinate transformations in some sense. I mean, in the sense that you have the same polytope, and the choice of what amplitude you get depends on this diffeomorphism. No, we don't know that actually. So interestingly enough, if you take, let me give one example that Nima and Song and Carolina found, and maybe I will end with this. Unfortunately, I couldn't put it to Yang-Mills. But let me just give one example which I found quite striking of the same type. So we don't know. To answer your question is we don't know. In fact, I think most of the diffeomorphism probably won't give us amplitude. But let me tell you one which was very surprising, which is that you consider Xij to be Xij minus epsilon, or maybe let me put lambda, for ije1, and Xij plus lambda for ij odd, and Xij for if either of them are, if I is even, I and j are not both same, I even, j odd, etc. Now you do this map that we just told, and so you'll get some complicated function of lambda, etc. So let me just write some deformed thing, let's say some deformed function. So this is a function that multiplies the dx's. So I'm just writing the function, which is a function of lambda and some x13, x24, etc. Now you take this and expand it, take large lambda limit. So do a large lambda expansion. So you would expect, okay, large lambda means, that means you will get some low energy theory. So you say that I want to take all the x's, for example, x13 to be much less than lambda. So I expect some EFT. This deformation gives you nonlinear sigma model. So that means that somehow the same associahedron polytope which with identity diffeomorphism gave us amplitude with no derivative interaction, but for some diffeomorphism, and it gives us precisely gives for any nonlinear sigma model amplitude at tree level.
I didn't understand why you said most diffs won't give something. Here you explained that locality and unitarity were encoded.
Yeah.
Because you had simple poles at the boundary.
Yeah.
It seems to me almost any function I write down which has that property of
Yeah.
unitarity and should be an
Yeah,
amplitude.
yeah. Sorry, what I meant
so
is
why do you say
not
that
linear ones. Linear ones we expect to give. So Mrunmayya looked at all kinds of crazy examples of beta alpha. We always found some Lagrangian which fit that theory. Okay. But I think with nonlinear we don't know. Because nonlinear
why won't the argument still work? It has simple poles and it factors.
But remember that this polytope is always, I didn't have time to explain, it's always living in a positive region. And so now if you look at some random diffeomorphism, let me say I don't know the answer. I mean, we don't know the answer. Like we haven't looked at them. We haven't looked at such. Yeah. Okay, we can talk later. I looked at some and it just doesn't give anything reasonable. But yeah. I mean, sometimes it can happen that some of these can collapse because of nonlinear diffeomorphisms and won't give us anything. Okay, I'm out of time or?
Yeah, we can have questions or if you want to go.
No, it's fine. I mean, so okay, I didn't go to Yang-Mills, but I hope to convince you at least I hope you were interested that there is this is a universal object and it's giving us a large class of amplitude, including amplitudes we would not think have anything with phi cube theories, like only a sigma model, for example. So and everything I said, it absolutely goes to verbatim at one loop because there are analog polytopes in which are called type D polytopes, and everything I'm saying you can look at our papers and Nima and et al. Papers also, where everything goes for one loop integrand, like absolutely verbatim. So okay, maybe I stop here.
Yeah. So when I read this work before, then I was under the impression that getting to the n-3 form, the omega form, required me to make some choices from the n-3 over two-dimensional space. And here that choice would have been included in the fact that when you wrote the formula for the form, there was the prefactor, and then there was dx13, dx something else. And those dx's that made it a two form, were they chosen or are they?
No. So yeah, so the way the original paper said it, they sort of defined the form before anything else. They said they wanted as you would remember, projective invariance, and they found some form. But you could have done it completely differently in the sense that you just look at this polytope and you simply ask, I want to look at a form which is meromorphic, which has singularities on all the boundaries and only boundaries. Then you precisely end up with the form that I wrote. No choice, no other choice, up to an overall sign. So that fixes the form because there are some, we can discuss later, there are some recursion between residues between one face and a lower dimensional face, etc. that kind of constrains that form. And so that's all we started with in here, like we didn't assume anything else at all.
So in that reading, it looked like that n-3 was a top form in some n-3 dimensional space. But
sorry. Oh, that's what, yeah, absolutely. This is a form which is, I should have maybe said that. It's a top form, absolutely. So I want unique top form, given a polytope of dimension D, there is a unique top form, a unique form of dimension D, which is defined in a bigger space, of course, because Kn is big, much higher dimensional. But the form has the same dimension as the polytope itself. Yeah, but that form is unique.
Two questions. One is short. Like, is there a position-based story of version of the story? Like, and second, like, even if you choose linear diffuse, but like, if you thought of these alpha edges as some average or something, like some probability distribution, do you expect anything meaningful?
So the answer to the first question, I don't have a direct answer, but I can give you a sort of little indirect answer that at least for tree-level amplitudes, for phi cube theory, this formula is same as if you have heard of CHY formula, which is this worldsheet formula. And Sebastian and his collaborators wrote that if you want to look at phi cube amplitude in ADS, like a position space Witten diagram, it also has a worldsheet formula, exactly CHY formula. And so from that perspective, I would say that yes, there will be the, so this Associahedron is diffeomorphic, but with a very complex diffeomorphism to the moduli space of punctured Riemann sphere. So that part doesn't change, but what changes is the integrand for the ADS amplitude, which is position space. So answer to the first question would be yes, but I don't know beyond the Sebastian's work, anyone has looked at it. Second one, I don't know. If you average, I don't know. Yeah, I mean that would be like, because these betas really go into the coupling. So I didn't have time, but you can ask what happened to betas. So the alphas basically go into the mass spectrum of the theory in this way, and betas go into some ratios of these couplings. So that would be like asking if I do like S matrix over couplings and average what I get. I don't know, I mean that, I don't know if you get anything reasonable. I think Komargotsky has some paper like this, but I don't know the result, what they found. So yeah.
It's the broad, I mean, so at tree level you have one polytope, at one loop you have another polytope. Is that how it's supposed to go?
Yeah. But they are these universal polytopes. I didn't have time. I can give let me just give an answer for tree level first. That the story at tree level is the following: that if you take this polytope, which is fixed because it's not in our physical space, then its deformation gives us different couplings, like different 5-cube couplings like this. If you translate it, we get different mass poles at different masses. And if you project it, like you go to some lower dimensional projections on this, we get higher order interaction, like 5-4 interaction, etc. So there is a way to encapsulate different interaction at cubic level, different masses, and higher order polynomial interaction by either projecting, deforming, or translating this polytope. That's 3 operations. And that goes through at, like, so if you take one loop, for a one loop integrand, there is a polytope. And the same operations will give you integrands for large class of theories like this. Absolutely, that's a great question. So if you look at this one loop polytope and its boundaries, many of the boundaries are associahedron. So that structure is encoded in the polytopes. Yeah.
And then because the theory dependence comes in various deformations.
Yeah, right now it looks like they come in these diffeomorphisms, exactly. Yeah, that's a question that I find a bit puzzling. Like, yeah. So it seems like there are these. Exactly. I mean, that's surprising, right? That somehow we could relate. We would not have thought of this, right? S matrix of 2 different theories already at tree level in terms of some diffeomorphisms like this, right? I mean, that's a very. I mean, so there is some sort of seed geometry which is universal and it spans different S matrices which are not unitarily equivalent to each other. Okay, maybe stop. Yeah.
Thanks,
Sorry for going over time.
Alok, and let's thank Alok.